Yeah, I decided to.
Okay. Well, it's about time to start. So today, Zhang Jiang is going to do his student presentation, and he's basing it on one of the data sets from the homework, and you know, to illustrate some of the things that he did with that, and connect to some of the topics. All right.
Hi everyone. I'm, I'm going to do the wage and race 1987 analyze. And the easier way to start analyzing would be finding the relation between numerical and from common sense to see the expertise education would be related to income. So I start to find the correlation between these three variables. However, from the graph and chart, we only see the negative linear regression between expertise and education. That may be because if one gets more education, it will be less time for practicing skills. So I interact education with expertise and create my first linear regression model. Then I found the negative linear correlation is only an illusion. There is no significant p-value. And after adding the variable of race, the result becomes better. And we see that the impact of race has significant at 99% confidence level. But the multiple R square is only at about 1%. So maybe we should add some other variable. Considering different areas have different income, I add regional factor to my most 3. And we found that the region of Northeast also significant at 99 confidence level. So it makes me think about the great migration of African Americans move from the rural south to the urban northeast and midwest and west area. And from the graph, we can see the connection. The place that moving a lot African American also have significant income increasing. And so we would come up with a question. Does this region also equality for different race of people in weekly earning? Like if not, why they all move to this area? So I interact race and region and create mode 4. The result shows the income difference is higher than any other area. And this makes me think about the 80-20 rule, that few people control most wealthy. And for the richest region, the inequality of wealth also become highest. And after analyze the variance of the log of mode 4 and compare with mode 3, like mode 4 has more significant value, so I keep the mode 4. And this is the graph of mode 4. And maybe because it has a very low R square value, so the graph doesn't show, doesn't make a lot of sense. And for my conclusion, I failed to create a reliable relation equation for predict weekly income. It's maybe because the income for a person is complex, not only because of its education or skill or age, maybe also connect with their fortune, like the friends they make, the family they come from. but we do have some. We do see some conclusion. Is the equality between race. It did exist, and also the income differential by region. Yeah, that's all. Thank you.
Before closing, can you go back to the plots, the residual plots and things from that model, right? So this is just plotting mod 4, and it gives some extra things. We didn't really look at those too much, but it's right. So, but what's in there? So one's the normal residual plot. Looks a little bit non-normal, right? Because right, well, there's some outliers and some extreme values. The income was kind of skewed, so it's right. And the next one, right, leverage and standardized residuals, right? And so the ones that have higher leverage on the end, like up there by 0.3, are into, there's a lot of observations, right? What was it? This one was 25,000 people or so it's hard for one observation to impact that so much. But a few up there that probably have the extreme incomes would be far enough out there that maybe they would do something. Right. And the standardized residuals. So some of them, standardized residuals up by 3, right? So a z-score of 3, -3 is kind of big, but out of 25,000, if we had a z-score of 4 or 5, I guess that would be a really bad prediction. But it marks a couple up there that have higher leverage, higher residuals. Yeah. Right. And then standard square root of the absolute standardized residual versus fitted values. Right. So, right, what would that be useful for? Right. So fitted values, absolute standardized residual. Right. So now everything's positive. Right. So if you saw large changes in that, in terms of the height, you could have very unequal variances of residuals, but it's not so much there. The larger values, I guess the bigger spread in the original plots were down at low values, right? They had low education, low experience, but still a big range, right? And then it kind of narrowed in the graph. So, yeah, tough problem. Did you think about anything else for this, dealing with the plots? So sometimes we look at, like transformations, right? So maybe log of income or something like that. Could possibly be done. But anyway, any other questions or thoughts about that? Did anybody else look at this one and think about transformations or?
I actually did some log, but it doesn't make a lot of sense. So I
it didn't work as well. So. Good. All right. Well, thank you very much.
Thank you.
Thanks for incorporating a little history and social commentary. Part of the point of looking at those data sets, I think. Great. All right. So for the rest of the day. Oops, 10:21. Still forget. So you're working on the projects, right? The homework 7 I'm going to postpone, right? So there was a listing on the original syllabus that there'd be a homework 7 due this Friday, but we're just kind of starting into things with ANOVA, so it doesn't really make sense to have one due on Friday while you're finishing up the projects. And initially the projects are due on Wednesday is the plan. I anticipate, some meeting maybe an extension to Friday, but if you get them done on Wednesday, that would be super. But so we're going to postpone this one and essentially just move it to the next Friday, right? Because that gives more time to think about ANOVA and its different varieties and do something more complete with it. So that's the big schedule type of thing. Right? And I'll have regular if you want to talk about, I will be in some on Tuesday morning primarily, but the rest of today I'm in, and then some Wednesday morning or via email if you've prepared a project, have some questions. If you send me a copy of it, I could look at it and at least give some initial feedback to see if I see something. But that's a big topic. So we're moving on into the course. Chapter 13 has two-way analysis of variance, right, where we're going to basically use analysis of variance and a linear regression version of that to model outcomes, right? And we're going to have a couple discrete factors together, right? And so the examples in chapter 13 are both really examples of randomized block studies where we have a treatment factor. Right? There's also something called a blocking factor. Some analysis of variance is two factors, have two different treatments together, and we can look at some examples where we have two independent, two different treatments going on and interacting with one another. But this one would be a very common design where you have some blocking factor and randomization happens within that, like we'll explain. Right? So we could say that the other things that the upcoming things we'll do things with two or more, but two treatment factors together. Really, we can look at things that have multiple treatment factors going together in a lot of design or agricultural experiments, educational experiments, others, industrial ones. There would be multiple things that you could manipulate or influence all at once, and we might do all those together and know what type of combinations together would be good. Another thing that's going to be coming up, related to this, is many of the things we're going to look at first are fixed effects. The effect of the treatment, the effect of the blocking factor, and we're just going to have indicators to indicate each of those. But once you get many blocks, right, or you get replications within different groups within those, random, sometimes some people would view some of those things as random effects and put a distribution on them. So that will decrease the number of parameters we use, but it's a different distribution, further distribution assumption. So we'll kind of see variations in there. So within this two-way ANOVA, really there's a lot of different things that get covered. There's kind of a model selection as well, and model checking. There's going to be an underlying model that has normal errors, very much like regression. And if our data doesn't look like that, then there'll be some questions about whether you should be doing this or using other methods to try to evaluate the effect of the treatments. Right? So this is kind of a big area, and we'll touch on a few different varieties of it. But some fields, psychology, other behavioral social sciences that might be doing experiments, education, and so on. Well, also, just industry as well will have whole courses on different ways of doing designs and trying to set things up to efficiently get information about many different dimensions of a problem all at once, right? And not just a single thing. So I think it's worthwhile talking a little bit about the case studies that are together. So in this case study, this is about seaweed and grazers, right? Fish and limpets and other things in the sea that eat the seaweed. So they kind of go around grazing on it, right? They have plots that are 100 centimeters on each side. So decent sized plot there. And they clear off the seaweed. Graduate student, as part of the dissertation, cleared off the seaweed and set up a cage that lets certain types of organisms into that area. Right? And there are limpets, which is capital L's, small fish and big fish. And so if they're all allowed in, the treatment is capital L, lowercase f, capital F. But they can set things up so they only allow in fish, or they allow in limpets and small fish, but keep out the big ones. Or they can set up only to allow in little fish, or just the limpets, so they keep all the fish out. Or they can just totally close it off, so that nothing gets in there. So they have, in all, 6 possible treatments on that area. There's a couple combinations they don't do, because they can't keep out the small fish. They can't keep out the big fish, but they can't. If you allow the small fish in, you can't keep out just one type of fish. You can keep out the big fish, but if you allow the small fish in, you can't. I don't know. So one of these, if you allow the big fish in, you can't stop the little fish. Right? So once you allow the big fish, the big fish in, then the small one. So this, there's a couple that are not possible in this. So LF and F are not possible. You can't allow in the big fish and stop the small ones. So you're always at little f, big F, if you're going to allow F. Right? And so there's these 6 things. They are going to have 8 blocks of 12 plots. Right? So each block has each treatment 2 times. Right? And so these blocks are how the things are organized in the water. Right? So you have a shore coming down like this. Here's the water, and you get some area in here, right? And you're going to put a bunch of these plots, right in there, a certain number, and they're kind of at this area, right? And then you're going to have another group over here, and then somewhere down here you're going to have this next one, right? And so each one of these is a block of plots. So it's a physical thing of how this thing is set up, right? The idea of having the blocks is, there's some organization to how it's placed there. The growth of seaweed is going to be different, probably, you would think, maybe, at these different levels, right? There's more sunlight up here. It's different elements, there's different things living in different places. So there's some part of the variability in seaweed growth that would be captured there. And you apply each of the treatments a couple times within each of those blocks. So maybe this is number 1, 2, 8, and there's some others spread in there in different ways. The book, the description doesn't say that they're necessarily in a strict order. There's kind of rocky areas, sandy areas. That's a little hard to figure out how they would be ordered in any meaningful way. And so the randomization happens to each of these little plots in terms of which treatment they get. There are different factors that are involved in the experiment. There are treatments. Right? There's 6 that are being considered, but these blocks are another thing affecting the measurements. And there's 8 of those. The outcome that they're going to look at is the percent of regeneration of seaweed after 4 weeks. Right? And they kind of have a novel way of measuring it. They go down underwater, maybe scuba diving, not a bad activity, and they put a thing over this 100 centimeter area that has little holes in it, right? And they can look down through the hole and see if there's seaweed growing there. Right? So if they had underwater cameras, maybe they take a picture of each one, and then maybe you have the computer try to do it, but this is more manual. They maybe have 100 little spots to look through, 10 by 10 in each of those, and they can look through and say, okay, 72 of them have seaweed growing in them, right? Just kind of yes or no. So they'll get an estimate of 72%, right, for that one. And they do that for all of these blocks, so 96, 8 blocks, 12 plots, and 96 plots going under there. And then, they have to make a judgment. Is it seaweed, or is it just a little green? Is it really qualify? So that's a biology choice. If they know, it'd be kind of hard to do blinding. If they know that there's nothing allowed in there to eat it, if they know it's completely closed off, can they really be objective in measuring that? It's a little challenging. While there's other ones where they have all the organisms in there and there's a little green fuzz down there, can they be objective and say that there's nothing going there, right? If they had an underwater camera, they could take a picture, kind of have a record, and that could be verified by somebody. So the outcome in these things, I guess I'll try to get it here, right, so the outcome of this one, right, is R is going to be a percent of blocks that are covered with seaweed to a certain degree, and a percent that are uncovered. So it's a ratio of proportions, and actually they use the log of R, which is a certain equivalent to a logit transformation of the percent that's covered. Right? So they do a certain transformation, and a log of covered over uncovered is the logit in this case. Right? Ultimately, they come up with a conclusion that there were actually little block effects, so maybe the picture wasn't quite as extreme as my picture might imply, but there weren't many block effects, but the presence of species did matter, right? So they can test those, both the blocks, the treatments, and then they can look at an interaction. Did certain block types get affected by the species in terms of their recovery, right? So that's one design setup for this. The 1302 case is studying something called the Pygmalion effect. Right? And so this is an expectation effect. Right? There's a famous book by Buck Rosenthal called Pygmalion in the Classroom, that if teachers show or express expectations for students, often the students live up to that, good or bad, right? So if some students are made to feel like they're not as good, it's almost like a self-fulfilling prophecy. And so it can happen in complex ways, and been tested many times, but people do respond to their what's expected of them. And so if you deal with people of different backgrounds or with disabilities in a way that's suggestive that they're not as good or have less expectation that they will achieve at the highest level, it's a serious issue. And in this case, they studied 10 military companies. So these would be groups of soldiers. In each military company are 3 platoons. Right. So 3 sets of soldiers within each of 2 companies. So there's 30 total. And a platoon was randomly assigned to be treated a certain way. Right. So the randomization unit in this case is 30. Each platoon has many individuals. And so each platoon is going to get a score based on their performance. Within each of these 3, one of these was randomly chosen to be treated special, right? To be told kind of indirectly, to have a leader in the platoon be told that the individual scored well on a psychology test, right? Personality test, in terms of their behavior and attitude. Not on the thing that they're going to be evaluated on, but on something else. And it was communicated not to everybody there, but to a leader. So the question then is, does the chain of communication impact things through that, right? Two of these were just treated as regular, right? And they did something called a practical speciality test. This is a test about the weapons that they use in terms of their performance and knowledge of them. Right? And so again, this becomes a randomized block study. Right? And so the blocks in this case, right, are the 10 companies. And then within each company, they do both treatments. Right? And the units are randomized to the different treatment. And then particularly in this case, there was one that gets one treatment and two that get the other, so you don't have to have those things equal in there. Right, 10 companies, each block has 3 platoons. Right, that's the structure we know about the population. And the treatment, the other factor that's at play here, right, is treatment. And kind of the Pygmalion test group. Right, versus the 2 regular ones. So the treatment that we're interested in, and there's these blocks that are used for randomization, right? And the outcome, right, is from that test. So kind of the average score for a platoon. Right? And the conclusion of this one is that there's a very large impact of treatment, and I think very little block-to-block variability was there, but there's a very large impact on their performance based on that. Right? So it's kind of different than multiple, two-way ANOVA maybe presented in some introductory books, that it jumps to this randomized block, which is useful for many designs. Right? So you have to keep track of blocks, treatments, and then the outcome. Right? In this one. Before, what would be an advantage of using blocks like this? Right. What enables us to use blocks in these 2 cases? Right. In some way, we can divide up the population, right? We can divide up the population by these companies. What does a company do? I don't know. Does it have people that all start at the same time? Are they in regional areas? Are certain companies exposed to, going to service someplace together? Maybe the 3 platoons that are in a particular company have something in common that affects their training and experiences, right? So they're kind of similar in some ways. And maybe the platoons are different from each other. Right? So if you just purely randomize platoons, you could end up with all 3 platoons in one company being treated as regular, and 2 platoons in a different one be getting the Pygmalion effect, and so there'd be a lot more variability. Right? But with this control, that it's 2 and 1 within each of those, then at every different kind of military company experience level, whatever that entails, you get both treatments in a very controlled way. So it should make the outcome and the measurement of the treatment effect more precise, because it controls some variability. Right? Same thing for the sea grazers. By having these different plots, there's reasonable belief that there could be variability in there. If you just randomized there's 96 plots altogether, and if you had each one has a treatment 2 times, and there's 24 of each, 2 times 8, 16 of each of these treatments. If you just completely randomized, you could end up with the LFF, having multiple ones up here, having none, have multiple ones down here, and it still would be a randomized experiment. So on average, it would give you the comparison, but it'd be a lot noisier, and it would be affected by how the randomization actually went. Right? Randomization, on average, removes biases, but in a small sample case, you can still have differences. Right? You could put those things into the model to try to adjust for them, but it's often better to do things through design and randomization rather than trying to do it after the fact based on statistical adjustment. Right? So usually, if you can do a design that has more control, you have a better chance of seeing something you want to see. Right? So, we're going to model these data, right? We're going to have one model is just an additive effect model. Okay. Sometimes it's just called an additive model. So we have Y, I, J, K. Thinking about the Pygmalion example. Right? So if I indexes treatment, right, and J indexes blocks, right, which in the military example are companies, right, and K would be then the individuals. I'm trying to make it too small for this thing. Individuals. And these are the platoons. There was 30 platoons, right? So that response that we would see for a certain platoon, from a certain block, getting a certain treatment, can be written as there's a main effect, kind of an overall average level, plus treatment effect, right, plus some block effect, plus potentially some random error. Right.
Is that a J for the treatment?
J for, I for treatment. J, I reversed order in my treatment. This one should be J, right? J. Right. Yeah, J for blocks, I for treatments. Right. Right. So there would be different values there depending on which I or J would be there, right? And if you're in a particular treatment, you add those up, right? The book writes these. The treatment for block, it calls this a beta 1. Right? And so you get that if you get the treatment, the Pygmalion treatment, at a 0 otherwise, right? And these, it gives values 0, beta 2, beta 3. So it's either 0 or beta 1. And this is beta 3, up to beta 10, because there's 10 companies, right? And so in this model, the number of parameters that you're really dealing with is there's one for the intercept, there's one for the treatment, and then there's really 9 others to indicate these 10 groups. So that would be 11. There's an error variance. Generally, in ANOVA analysis of variance, the EIJKs are going to assume to be normally distributed with mean 0 and some variance sigma squared. So like the other ANOVA models or regression models, there's a constant error variance, right, and normal. Right? There's another way of writing this model like we might use in regression. Right? We can put some indicators in there for some indicator variables that have which treatment you're getting, which block you're in, and make it a little more explicit. Right? so to write that, we're going to have an indicator for treatment, and we're going to have an indicator for all the blocks. Right? And instead of just kind of implicitly saying, well, if you're in treatment I, you use this one, and if you're active treatment or placebo, and if you're in the groups, except for the first group, then you have these other ones. The model can be written as it's beta 1 times an indicator. This one equals 1 if you're in the treatment group, and it's 0 if you're in control. So in this case, the control is just the platoons that get the regular treatment, and the treatment is the ones that do that, right? So, and then to indicate these 10 different troops, right? Not the troops, but the companies. We have a beta j times an indicator for this. So I sub j equals 1 if you're in company j. Right? Otherwise, it's 0. Right? Plus this error variance, or the residual on there. Right? So some text and some fields writing about analysis of variance, we'll write things out like a model where which group you're in is really kind of implicit in understanding where you come from, right? And so the group membership gets encoded kind of behind the scenes through that notation. Right? Another way of doing it, like you would typically do in linear regression, is to put the indicators there, right? So that kind of switch from creating a variable that indicates something versus kind of implicitly having it in a subscript or a superscript somehow in there is kind of a change in how you look at things and how you write down models. It has some value in terms of missing data. For one thing, if having something explicitly as an indicator, is it there or not, gives you a variable to work with. So you can think about variance and mean, and it's kind of been an important thing to development of methods for handling missing data. It's not just thrown in there as kind of something here that would say observed part, unobserved part, or something like that. And kind of hiding part of the, not hiding, but just kind of obscuring some of the things there. But actually having a variable there does help with thinking, I think, about some things, right? You should still have the same number of parameters, so 1 here, and then there's 9 here, because you can leave out the one group there. So that's just an additive model. And as you get a different effect, right, for a military company, which is the blocks or the treatment, you add that in. But there can be an interaction. Right? Treatments can have different impacts in different blocks. Right? You can have interaction between treatment and block. So that would say that the impact of the Pygmalion effect has a different impact in different companies. Maybe some are, there's individuals involved here. So maybe the individuals involved in some companies are better at avoiding maybe a negative effect, or maybe they just kind of champion everybody and pull everybody up and don't have that impact. But in others, there could be a bigger impact. So there could be an interaction. Right? So the interaction model is going to be, our yijk's would be the same outcome and intercept. If we write it this way, there's the treatment effect, there's the block effect, and then there's going to be an interaction that has both I and j subscripts. I is treatment, and this is block, and then there's potentially some error here. So if you're in treatment in a certain block, you would have this extra bit added onto the score, and maybe it makes a particular difference in some of the blocks that you're treated like the special one versus not. So you can have a difference there. We don't have many replications in this study, right? Because there's only one Pygmalion and then 2 of the others. But so we've almost used up all the degrees of freedom there for testing things. That's something we'll talk about on Wednesday. How do you do testing in all this, right? If we do this in the regression context, right, we'll have, beta 1 times an indication for treatment, plus we need a number of indicators for the blocks, beta j, I sub j for block, right. Plus we have this interaction, beta, 1j, right, j going from 1 up to, 2 up to 10. We take the indicator that they're in treatment times the indicator that they're in a block and put that in there. Right. I'm going to clean this up just a bit. That's a 2, that's a 1j. So if block J, so military company J, the platoon that gets the treatment gets this extra bit added on there. Okay. And so this model has, the intercept plus the effect for treatment plus those 9 for the block effects plus this 9 for the interaction. So this one actually has 20 parameters. Plus the assumption on the error variance as being constant, so there's really 21 parameters to estimate in all. We only have 30 observations, so it's getting kind of lean to estimate that, right? So how would analysis of variance go in general? What would be the general kind of overall analysis plan? We'll talk about details of significance testing and the F testing, and then how it gets done in R on Wednesday, right? So what is the overall analysis plan that we would like to use? So you set up your study, gather the data, and the first thing to do would be to look at the distribution of Y, your outcome. What does that look at? And you could look at, are there differences by these different factors? Does Y differ a lot by block? You might do side-by-side block plots for these different groups, right? Histograms of the different groups, and so on. So graphs. You might look at tables of means. Do they differ by block? Does there initially appear to be any treatment difference by treatment? And if you have the block by treatment groups, that interaction, you look, is there an average difference of Y across those, right? The interactions. The interaction of block, times treatment. Right. Are there average differences? If it's really skewed, maybe you want to think about a transformation of Y. The outliers. So we're going to look at average differences. Average differences, maybe a transformation. Are there averages? Are there any enormous outliers there? If one of the military companies got, in the single digits for percentage competence, and all the others are getting in the 70s and 80s, well, that would suggest that there's something really funny going on. Either that company or that platoon was a special one and was not trained on those things and have no idea what they're doing, or the data values are misrecorded. I had some ancestors back in the Civil War who were musicians, and so When they were in the Civil War, their job was in the musician corps. So maybe they were trained also to use weapons, but they certainly, there certainly are different groups in there. So if things look all right, you're happy. Maybe we've taken the log transformation or logit for proportions, right? Then we can do an F-test for the interaction. All right, so we'll start with the larger interaction model. We'll look at some cases in chapter 14 after this one where you have a small number of observations and you don't really have enough to fully estimate an interaction and an error variance, right? You get kind of one observation per interaction, and therefore you don't have anything left over to estimate error variance. There's a special case there, and so we might need to do a little bit of modification to this plan in the no replication studies. Right? But if we can do this, if yes, interaction significant. By yes, I mean interaction significant. Right. Then report this. Then report that result. Right? So if it's a significant interaction result, you can report that. Right? And after testing for the interaction, so this might be reported, illustrated with graphs and so on, saying that there is a treatment by block interaction is statistically significant. That's important to know. You can do tests then for the overall treatment. If yes, right. After this, there's an F-test for treatment. Is there a significant treatment effect overall? And this one has to incorporate the interaction in a certain way. Right. So it's really a test of the treatment effect, taking both the main effect of treatment and an interaction into account. So it's a more expansive test. But you can do that test. Right? If the F-test is not significant for the interaction, then we don't report that. So the interaction wasn't significant. Then you fit the additive model. You can take the interactions out, the additive model. Right? And then we can report F-tests for treatment. The treatment main effect. Right? To see if that's significant. And beyond these tests, we check assumptions. Right? We can again look for outliers, look for normality of errors. Right, again, look for outliers within groups. Outliers, non-normal. Think about, has this gone well? There, it's possible to do a randomization test. So if you do have some questions, like there's some outliers that look kind of big, particularly for a small sample size, or distributions that are a little bit less normal than you feel comfortable with, there's a randomization test, and that might confirm some of the F-testing from the p-values. From that. But beyond that, there would be linear contrast of various sorts. Right. This is really, illustrated with the seaweed example, right? Because you can look at the impact of, you know, the large fish on seaweed regeneration, or a small fish on seaweed regeneration, right? Or if you have both, two are there but one's absent, does it make much of an impact? Does it make much of an impact if you could divide the blocks up to, you know, an intertidal zone and then a lower zone or something like that, or a rocky area, non-rocky area? Those type of specific questions would be framed as linear contrast between the different outcomes. And if you have overall significance, then you can write it, you know, kind of drill down, as they say, and find out where those differences are and express confidence intervals for those. Right? That'd be kind of the overall right analysis plan. In the seaweed example, there's really 3 treatments plus blocks. So this could be called a 4-way analysis of variance, if you think about it. Right? There's whether you let the limpets in and crawl around, and if I'm thinking of the right thing, and eat the seaweed. If you can keep out the big fish, but the others get in, right? And if you can keep out the small fish. Now, 2 to the 3rd, right, is 8. Not all 8 are actually possible because they don't have a physical device to keep out only the big fish, right? You know, or keep out only the small fish, right? So you let the small fish in. Well, you let the big fish in, and the small fish are going to swim in too. Right? You can't get them all in there, right? So this might be thought of as multiple, and kind of the fact that it has the treatments can be broken down into these really kind of opens it up to these linear contrasts and doing more things, right? This one would be called an incomplete factorial design. Because only 6 of the 8 are possible due to physical constraints. Right. If all 8 were possible, we would call it B factorial. You know, all levels of each treatment in combination with all the levels of the other treatments, and it's called factorial. It's nice to have that when it's possible, but a lot of times you're due to resource constraints or other things, only getting some of them. Sometimes you have to make choices. Which of the contrasts do you really care about? Right? Which treatments levels should be contrasted to others, and if you care about them, then you should have some direct observation of it. Other ones that you would never consider, you might leave those out because they would be something you ever think about actually doing or using, and it might have you reduce sample size. But you still got to figure out, can you do the testing, and so that's where it gets kind of complex. Right? And just to finish up, not all 2-way ANOVAs are going to have blocks, right? So thinking in examples in diabetes care, say you had individuals who were diagnosed with diabetes within the last year. For a medical study, there's usually some type of entry qualifications. Eligibility is another word that's used. Eligibility. Individuals can't be too sick. You know, with other complications that might be life-threatening. You're not going to put people in exercise programs if they've recently had heart attacks and things like that. So, they'd also have to consent to be involved and available for the time frame of the study. And so you could imagine having some drug interactions for the individuals. Metformin is a key frontline drug used in diabetes care, but often metformin is combined with a second drug. In part, that diabetes is high blood sugar, but it can be caused by a number of things. It can be lack of production of insulin, or the insulin being produced, not being used by the cells, and just some other processes. Right? And so sometimes metformin will lower blood sugar, but the second drug will sometimes help with the other processes. The insulin that is there, there's drugs to boost insulin production, there's ones to boost insulin absorption, and so you get different things. But there's also lifestyle intervention. You could have a light amount of lifestyle intervention, just kind of some counseling a couple times to give people information about reducing fat, reducing sugar, getting up off the couch, and things like that. Or you could have one that's more intensive, where people would actually be put into classes and have more follow-up, right? So in this case, there are two levels of each. So if you combine those, there's 4 treatment regimens. And say you had, after consent and eligibility, you had 6,400 people. Right? You could randomize 1,600 to each treatment. Right? And that would be a 2-way analysis of variance. The 2-way ANOVA model, you could again have the YIJK, and you can have some for metformin effect. You can have a lifestyle effect, so metformin, lifestyle, and you can have an interaction. Plus some potential error, right? There should be if randomization works out evenly, there'd be 1,600 people in each level, and it very much looks like a linear regression model with those factors. So that might be how it's designed, right? And again, this will be called 2-way ANOVA, so some of the formulas and things that we'll do will apply to that. But in a study like this, with this many people, you probably have other factors, right? And even though it might not have been part of the randomization design, right, you might want to adjust for factors, either discrete or continuous. So if your outcome is something like blood glucose levels, fasting blood glucose levels after 3 years of treatment, or 1 year of treatment, you might put a continuous predictor in here that's baseline. What were the people at the start? Some are just over the threshold for diabetic, and then some others that are just way off the chart. They're just very, very high. So their initial point, right, so surely would influence where they are a number of years later. Sex, males and females interact could be different. And for an indicator like that, you might have an interaction between treatments, right? Age groups. So the ANOVA is a special case of models that are useful in many contexts. But many times when you get into big data sets, complex questions, and you get a lot more variables, you start transitioning into regression if you want to use more variables and study more phenomena. Right? So on Wednesday we'll come back and look at some of the R code for doing this or a similar model in ANOVA. What are these F tests and so on. Hopefully this kind of puts there's kind of enough complexity in those chapters that just having a day talking about the models and the data, I thought would help with the needs of that. Great. So see you on Wednesday. Right, write up some notes. Talk about that. Thanks. Thank you. Yes. After 12:30 today. Let me. Why don't you come by? I'm just trying to think. I know I have some advising meetings coming up. I think a student's coming about 12:40.
So last stickers are like luxury.
5. She's gonna come about 12:15. 12:20, 12:15. Then we have about 20 minutes for the student advising. Okay. Good.